before we get into the graphing, I want to introduce you to function notation. And function notation begins like this. So it replaces the y equals with f of x. So f is a function of x. So we say f of x. And if we put it in slope-intercept form, it looks just the same as it always does, except for with an f of x instead of y. So if my equation were f of x equals 3x minus 15, then my output is still 3 times my input minus 15. So if I wanted to find when x is negative 3, what the output would be, I would write that as f of negative 3, and I would evaluate it the same way. I'd put in negative 3 for x. And so I'd have 3 times negative 3, which is negative 9, minus 15. So f of negative 3 equals negative 24. So what that tells me right there is that when negative 3 goes into my function, negative 4 comes out. So that's how I write that my input is negative 3, my output is negative 24. If I were given a function f of x equals 2x minus 10, and I wanted to find the input that would give me an output of 6, then I'd be looking for x so that f of x equals 6. So what I'd do is I'd take my original function and I replace that f of x with 6, and I solve just like I normally solve my equations. Add 10 to both sides, divide by 2, and I'd get x equals 8. So an input of 8 will give me an output of 6. So one of the examples in the book says the gray wolf population in central Idaho was monitored over several years for a project aimed at boosting the number of wolves. The number of wolves can be modeled by the function f of x equals 37x plus 7, where x is the number of years since 1995. Graph the function and identify its domain and range. So, since we're starting in 1995 and moving on from there, we're going to use positive x values. And since the population of something can't be negative, we're using positive outputs as well. So we're going to just look at the first quadrant of our graph. That means that our domain is for x values greater than or equal to 0, and our range is for f of x values greater than or equal to 0. So notice how we write our range a little differently. Instead of having y equal, we have f of x equal. Now, it is positive, but let's keep an eye on our range and come back. We might have to change that here in a second. So our output is in years since 1995, so we're going to go by single years. So our x-axis will be labeled going up by ones. However, our slope is 37, so that means our outputs are going to be going up rather quickly. So we'll start at 0, but let's go up by 20s. So our first output, year 1, or in year 0 actually, is 7, just shy of halfway to 20. After 1 year, we're at 44, so we're just above 44, or the 40 mark. Year 2 would be at 81. Year 3, we'd be at 118. So we can draw our ray from there. Now, like I said, our range might not be accurate because we know that we want positive outputs because we can't have a negative population. But notice that the lowest value our population hits is 7. So that means our range is going to be greater than or equal to 7. So this trend follows the function for the population of wolves. Now, another way we want to look at functions is by comparing them to what we call the parent function. parent function is the most basic form of a type of function. So for linear functions, the most basic function you can get is y equals, or f of x equals x. It has a y-intercept of 0 and a slope of 1. So if we're to graph that, we only need 2 points to graph a line, remember? We have an infinite line that goes in both directions. Now, every alteration we do to the function changes one of the aspects, either the y-intercept or the slope, or sometimes both. So for instance, g of x, just another name for a function, it's okay, we can switch whatever letter we want in there, except for we wouldn't normally do x of x because that'd be confusing. G of x equals x plus 3. Now that has the same slope, and now the y-intercept is at 3. And so if we have the same slope, we've created a parallel line 3 units above our original function. So that is what we'd call a vertical shift or translation of our parent function 3 units upward. So when they ask us to compare the graph, we'd say it's a vertical shift 3 units upward. Now, as I said, there's another way to change our function. We could stretch the graph or change the slope. So in this case, our y-intercept is the same value, 0, but our slope is now 2 over 1. And so we see that this function rises faster than our original function. It's steeper. And so you can call that a vertical stretch. And so when we see parallel lines, we see that they're just translations of each other. One is a shifted version of the other. And so one is always, if we have parallel lines and one is a shift of the other, one is always the exact same amount higher or lower than the other. The distance between them never changes. So the last thing I want to do today is give you a couple of examples to work on. I want you to take the function f of x equals negative 2x plus 7. And I want you to find the output when x equals negative 5. And I want you to find the input that will give us an output of 14. So give that a shot, pause the video, and when you think you got the answer, unpause and we'll check your answer. Okay, so to find our output when x is negative 5, we take f of negative 5, we replace the x in the function with negative 5. We get 10 plus 7, so f of negative 5 is 17. To find what input will give us an output of 14, we take and place 14 equal to negative 2x plus 7. We go through our steps to solve. We subtract 7 from both sides. 7 equals negative 2x, and we divide by negative 2. We get x equals negative 3.5. So our processes haven't changed, just the way the equations look have. If you have any questions, feel free to ask. You can go back and watch the lesson if you want to see something again. Otherwise, you can move on to your homework.